Hello and welcome to one and all. I am Miss Premal Popat and today we'll be studying the last module of the chapter Heat, and this is a 10th standard topic from Science and Technology Part 1. And in this module we'll be solving various sums based on the topic. So let's get started. The first example is how much heat energy is necessary to raise the temperature of 5 kg of water from 20 degrees Celsius to 100 degrees Celsius. So over here the mass is given as 5 kg. So what are the given things? Mass is 5 kg. C, that is specific heat, is 1 kilocalorie upon kg degree Celsius, and change in temperature. Now in the question, the temperature is raised from 20 degrees Celsius to 100 degrees Celsius, right? So what will be delta T? Delta T is change in temperature. So it will be 100 minus 20, which is 80 degrees Celsius. Over here, the energy to be supplied to water is equal to energy gained by the water. Now in the question, what is done? How much heat energy is necessary to raise the temperature of the water? So basically heat energy is given to the water, and in turn the temperature of the water is increased. So the energy supplied, that is the heat energy supplied to the water, will be equal to energy gained by the water, right? So which is nothing but mass into water into specific heat of water into change in temperature of water. So the energy, that is the heat energy supplied to water, is mass of water into specific heat of water and change in temperature of water. So we denote it as, that is the mass is M, specific heat of water is C, and the change in temperature is delta T. Just substituting the given values in the equation. Mass is 5 kg. So 5 into 1 is specific heat of water, and 80 degrees Celsius is the change in temperature. So the expression which we will get is 5 into 1 into 80, which is 400 kilocalorie. So hence the heat energy necessary to raise the temperature of the water is 400 calories. That means the heat energy given to the water is 400 calories, and due to this heat energy the temperature of the water is increased. The second example is a copper sphere of 100 gram mass is heated to raise its temperature to 100 degrees Celsius. So a copper sphere of 100 gram mass is taken and it is heated. When it is heated, its temperature has risen to 100 degrees Celsius, and then it is released in water of mass 195 gram and temperature 20 degrees Celsius in a copper calorimeter. So basically this copper sphere, it is released into a copper calorimeter where the mass of water is 195 gram and temperature 20 degrees Celsius is in a copper calorimeter. So if the mass of a calorimeter is 50 gram, what will be the maximum temperature of water? We have to find the maximum temperature of water in the calorimeter. In our previous module, we already studied about calorimeter, its construction and working. So on the screen we can see a picture of what is inside the calorimeter. So inside the calorimeter there is a container, and inside the container there is again a small container to keep a sample. So basically this copper sphere is kept in that small container, and outside the small container water is filled, okay, in the bigger container. So a precision thermometer is put inside the water to measure the temperature of the water. So inside the calorimeter, there is a sample placed in a sample cup or a small container. So copper sphere is placed inside this, and we have to find the temperature of the water when this copper sphere is placed inside a sample cup. So what is given? The specific heat of copper is 0.1 calorie upon gram degree Celsius, and that is why the specific of calorimeter will be also 0.1 calorie upon gram degree Celsius. Now suppose the copper ball water and the calorimeter attain final temperature. Like when this copper sphere is added in the small, is put inside a small cup. So after some time, the copper and the water and the calorimeter will attain some final temperature after some point of time, right? So what we can say, the heat lost by solid object will be equal to heat gained by water plus heat gained by calorimeter. Why we get this expression? We get this expression because a copper sphere which is heated is kept inside a small cup, and this heated copper sphere will transfer its heat energy to water and calorimeter, right? So heat will be lost by the solid object. So transfer of heat in this case will take place inside the calorimeter. So heat will be lost by the copper sphere, and heat lost by the copper sphere will be heat gained by water in the calorimeter. So basically over here water is the colder object and it will gain some heat energy and also the calorimeter, and hence we get this expression. So the heat lost by the copper sphere is equal to mass of the copper into specific heat of copper into decrease in temperature of the ball. Why decrease in temperature of the ball? That is the copper sphere. It is because the temperature of the copper sphere is decreasing due to transfer of heat from copper sphere to water and calorimeter. So what expression do we get? We get Q, that is the heat lost by copper sphere, is 100. 100 is the mass of the copper sphere. So 100 into 0.1, 0.1 is the specific heat of copper, and decrease in temperature. Decrease in temperature will be 100 minus T. Why 100 minus T? Because 100 is the temperature of the copper sphere when it is heated. So after some time, after the transfer of heat from copper sphere to water and calorimeter, its temperature will decrease. So its temperature will be decreased by what amount? 100 minus T. So similarly, we will find the expression for heat gained by the water. So heat gained by the water will be mass of the water into specific heat of the water into increase in its temperature. Why increase? Because heat is gained by water. So what expression will we get? So heat gained by the water, we will term it as Q1. So Q1 is 195. 195 is the mass of water into 1 is the specific heat into T minus 20. Why T comes forward? Because initially the temperature of the water is 20 degrees Celsius. So after some time its temperature will increase, right? And T is the final temperature of all the three things. So it will be T minus 20. And the heat gained by calorimeter will be same mass of calorimeter into specific heat into increase in its temperature. So Q2 is the heat gained by the calorimeter, which will be 50. 50 is the mass of the calorimeter into 0.1 its specific heat, and T minus 20. Again the temperature is 20 degrees Celsius. So it will be T minus 20. Now same temperature will be attained by both because same amount of heat is transferred to the water and calorimeter, because water is inside the calorimeter, right? So the expression which we get is Q is equal to Q1 plus Q2. Why Q1 plus Q2? Because heat lost is equal to heat gained by both, that is the water and calorimeter. So just putting all these expressions of Q, Q1 and Q2 in the equation, which is Q is equal to Q1 plus Q2, we get 100 into 0.1 into 100 minus T, which is equal to 195 into 1 into t minus 20 plus 50 into 0.1 into t minus 20. So after simplifying, the answer which we get is 10 into 100 minus t, which is equal to 20 into t minus 20, which is 210t is equal to 5000. So t will be 5000 upon 210, which is 23.8 degrees Celsius. So the maximum temperature of the water is 23 minus 8 degrees Celsius. Example 3 is as follows. Liquid ammonia is used in ice factory for making ice from water. If water at 20 degrees Celsius is to be converted into 2 kg of ice at 0 degrees Celsius, how many grams of ammonia are to be evaporated? So over here liquid ammonia is used to transform water to ice. Now the temperature of water is 20 degrees Celsius and it is to be converted to ice, that is 2 kg of ice at 0 degrees Celsius. So we have to calculate how many grams of ammonia are to be evaporated. The latent heat of vaporization of ammonia is 241 calorie upon gram. So the answer is amount of heat energy released. So the heat energy is released in cooling 2 kg water from 20 degrees Celsius to 0 degrees Celsius. Why is the heat energy released? Now the water is at 20 degrees Celsius. Okay. And we want to convert this water to ice. Since we want to convert water to ice, that is we want to transform water at 0 degrees Celsius to 0 degrees Celsius, the heat should be released to decrease the temperature, right? So the heat released is 2 into 1000 into 1 into 20. Why it is 2 into 1000 into 1 into 20? We know that heat released is equal to m, that is mass, into specific heat, which is C, into change in temperature, which is delta T. So what is the mass? Mass is 2 kg. So it will be 2 into 1000. Why 1000? Because kg I have converted to grams. 1 is the specific heat of water and 20 is the temperature of water at that point. So it will be 40,000 calorie. Now amount of heat energy released in converting 2 kg water at 0 degrees Celsius to ice. So how much amount of heat energy is released? It will be 2 into 1000 into 80 into 80. So 2 into 1000 into 80 will be 1,60,000 calories. Now we will have to add both these calories. Why? Because first heat energy is released in cooling the water from 20 degrees to 0 degrees, and then heat energy is again released in converting that water which is at 0 degrees Celsius to ice. So thus total energy required in converting water at 20 degrees Celsius is 2 lakh calories, and which is 1,60,000 plus 40,000. So how much grams of ammonia will be needed to convert water to ice? It will be 2 lakh upon 341. Why 341? Because it is the latent heat of vaporization of ammonia. So it will be 586.5 grams. Example 4. Equal heat is given to two objects A and B of mass 1 gram. Temperature of A increases by 3 degrees Celsius and B by 5 degrees Celsius. Which object has more specific heat and by what factor? So over here, so there are two objects, object A and object B, each of mass 1 gram. Equal amount of heat is supplied to both the objects, but the temperature of A increases by 3 degrees Celsius and that of B increases by 5 degrees Celsius. We have to calculate the specific heat of both the objects and compare which one is more and by what factor. The formula for specific heat capacity of a body is given as C, which is the specific heat, is equal to delta Q upon M del C. M del T. T is the change in temperature. So let Q calorie of heat is given to both the objects. So Q is the amount of heat supplied to both the objects, that is A and B. For body A, we'll take C specific heat as C1. So C1 is equal to Q upon 1 into T, that is 3. Why T is 3? Because the increase in temperature is 3 degrees Celsius for object A. So C1 will be Q upon 3 calorie upon gram into degree Celsius. Similarly, for body B, C2 is the specific heat for body B, which will be equal to Q upon 1 into 5. 5 is the change in temperature or the increase in temperature, which is Q upon 5 calorie upon gram degree Celsius. Now we'll just compare the specific heat of both. So for comparing, we'll divide the specific heat of both the objects. So we'll get C1 upon C2 is equal to Q upon 3, the whole upon Q upon 5. So QQ will get cancelled. This QQ will get cancelled and this 5 will go up and 3 will come down. So we'll get C1 upon C2, which is equal to 5 upon 3, or C1 is equal to 5 upon 3 into C2. Thus, the specific heat capacity of body A is more. Why it is more? It is more by a factor of 5 by 3. From the expression we can see that we multiply C2 by 5 upon 3. So the capacity or the specific heat capacity of body A is more than body B by a factor of 5 into 3. Example 5. A thermally insulated pot has 150 gram ice at temperature 0 degrees Celsius. How much steam of, that means how much heat energy will be required of 100 degrees Celsius to be mixed to it so that water of temperature 50 degrees Celsius will be obtained. So this example is same as the previous one, only over here we are converting ice to water and then heating. Previously the water was converted to ice and then it was cooled. That means the water was converted to 0 degrees Celsius and then it was converted to ice. So given things are, latent heat of melting of ice is 80 calorie upon gram and latent heat of vaporization of water is 540 calorie upon gram and the specific heat of water is 1 calorie. So the amount of heat required in converting 150 gram ice to 0 degree Celsius to water at 0 degree Celsius. Now over here we are converting this ice to water at 0 degree Celsius. So what will be the formula? It will be M into latent heat of melting of ice. So over here the formula is mass into latent heat of melting of ice, LH. So which will be equal to 150 into 80, which is 12,000 calories. Now the amount of heat energy required in heating 150 gram of water, which is at 0 degree Celsius to 50 degree Celsius. Now the water which is at 0 degree Celsius, we are heating it to 50 degree Celsius. So what will be the formula? It will be M that is mass of water into specific heat, C into change in temperature. So from 0 degree Celsius we are heating it to 50 degrees. So we'll get 150 into 1 into 50, which is 7,500 calories. So the total heat energy required to convert this 150 gram ice, which is at 0 degree Celsius to 50 degree Celsius, will be 19,500. How? We added both the heat energies required to convert water to, that is the ice to water. So it will be 12,000 plus 7,500, which is 19,500. Now what we have to calculate, let m gram be the amount of steam to be mixed with water. So we are considering m gram, which is the amount of steam to be mixed with water to bring the final temperature of the system at 50 degrees Celsius. Why we are calculating the steam? Because they have told us to calculate how much steam is required to be mixed. So the amount of heat released in converting m gram of steam at 100 degrees Celsius to water at 100 degrees Celsius. So over here, why is the amount of heat released? Because we are converting into steam. Okay, we are converting this m gram of steam, which is at 100 degrees Celsius, to water at 100 degrees Celsius. We are converting the steam to water. So basically the steam will give its energy so that it will be converted to water, right? So which will be equal to m into 540. Why 540? Because the latent heat of vaporization of water is 540. So which will be equal to 540 m. Okay, m we don't know the mass. We have considered m gram. Now the amount of heat released in converting. So again the amount of heat will be released in converting m gram of water, which is at 100 degrees Celsius, to water at 50 degrees Celsius. So students, here there are two cases. At the start we are converting this ice to water, which is at 50 degrees Celsius, and in the second case we are converting steam, which is at 100 degrees Celsius, to 50 degrees Celsius. So in case of conversion of ice to water, the heat energy is absorbed, right? And in the second case, the heat energy is released. So it will be again same, m into C into T, which will be m into 1 into 50. Why 50? Because change in temperature is 50. So again we'll get 50 m. So we will have to add both the heat released for converting this steam, which is at 100 degrees Celsius to 50 degrees Celsius, right? So total heat energy released to convert m gram steam at 100 degrees Celsius to water at 50 degrees Celsius is 590. Why 590 m? It is because 540 m plus 50 m. So it will be 590 m calories. So using the principle of calorimetry. Now what is the principle of calorimetry? It is the heat absorbed is equal to heat released, right? So 590 m is equal to 19,500. So what will be m? M will be 19,500 upon 590, which is 33 gram. Okay, so the mass of the steam is 33 gram. So students, this was the last module of the chapter heat, which was the 5th module, and this module we solved problems based on the topic heat. Thank you so much for your attention.